Welcome back to this series on topology. In today's video, we'll finish up our look at quotient spaces by focusing on their universal properties. You can find a playlist containing all the other videos in the series by clicking on the info thing that should appear right now. Before getting started, I'd like to briefly recap the definition of the quotient topology, which you can also find in more detail in the first video on quotient spaces. Recall that we used the following setup, so we had some topological space X, and some continuous surjective map Q going to a set Y. So this thing here on the left is a topological space, and here on the right we start with a set. Now the idea is that we would like to put some topology on Y that is described by the map Q. And the way we do this is we say that a subset U of Y is open if and only if the preimage of U under Q is open in X. Okay, so that's what the quotient topology is. Now, if you look at this definition, it does seem like a fairly natural thing to do, but you may be wondering why we're doing this at all. And this video will attempt to answer that question by describing the universal property that the quotient space enjoys, which will show how the quotient space behaves with respect to other spaces and continuous maps. From this perspective, it's basically the behavior of the quotient space that we're interested in, and this definition of the quotient topology just serves to make the quotient space behave in a certain way. Okay, so that was all fairly vague, so let's dive into the details. The first result we'll need for our discussion is a result that describes when maps out of the quotient space are continuous. For this, we suppose that we have a quotient map Q going from a topological space X to a topological space Y, and now we take some other space Z and consider maps F going from Y to Z. Now, the result states that such a map, F going from Y to Z, is continuous if and only if the composite F after Q going from X to Z is continuous. As always, it's much clearer to look at a diagram. So we have this setup down here, and what we're claiming is that this map F here is continuous if and only if this composite map is continuous. All right, so let's give a proof of this fact. First, let's suppose that F is continuous. Well, okay, since Q is a quotient map, it is in particular continuous. And this together implies that F after Q, the composite, is also continuous. This is simply because the composite of two continuous maps is, again, a continuous map. So that direction is really easy. All right, now conversely, let's suppose that the composite map is a continuous map. So we suppose that F after Q is continuous. And now we want to show that the map F is continuous. Okay, what does this mean? Well, it means that the preimage of every open set in Z is open in Y. So we take some subset S of Z, which is open, and we want to show that its preimage under F is again an open set. However, we don't yet know much about F, but we do know things about this composite F after Q. So what we're going to do is we're going to pull back S along the composite map F after Q. So we consider the preimage under the composite map of S. Now, since by assumption this composite map F after Q is continuous, we know that this set is going to be an open set. On the other hand, we can also rewrite this preimage as being the preimage of S under F, and then taking again the preimage under Q of the resulting set. Let's briefly think about why this equality of sets holds. So take some point X in the top set. Well, by definition, this means that X is mapped into S by the composite F after Q. So we know here that f after q of x lies in the set S. Okay, but f after q of x, by the definition of function composition, is just f of q of x. So this implies that q of x lies in the preimage of S under f. Again, by the definition of the preimage, because f of q of x lies in S. Okay, but now using preimages again once, this gives us that x lies in the preimage under q under f of S. Okay, so we've shown that if we have a point in the top set, it also lies in the bottom set. And now, in fact, these implications I've drawn, they go both ways because this is just the definition of preimage. So this means that if we start with a x in the bottom set, which lies in the preimage under q of the preimage under f of S, then this means that the composite map f after q of x lies in S, which is the condition for the point to be in this top set here. Now, why did we go through the trouble of rewriting this preimage like this? Well, it's so that we can use the definition of the quotient topology. We know that Y is endowed with the quotient topology, which means that a set in Y is open if and only if its preimage under Q is open in X. But now that's exactly the situation we have here, because here we have a preimage under Q of some set which is open, which now implies that this set here inside the preimage must be an open set in the quotient topology. So using the definition of the quotient topology, we conclude that f inverse of S is an open set in Y, and this is exactly what we needed to show in order to show that f is a continuous map. So again, we started with an open set S in Z. We used the composite to pull it back to X, and then it turned out that because of the definition of the quotient topology, this immediately implies that the preimage of S under F also needs to be open in Y. Okay, so all of this means that F is continuous. And that's the second direction of this equivalence we wanted to prove. Now, the reason this lemma is important is because in the universal property of quotient spaces, we'll be having exactly this setup, and we'll want to make sure that certain maps which we define out of the quotient space, that those will be continuous under the assumption that some composite is continuous. Now, there's a little bit more to this lemma, namely that the quotient topology on Y is actually the only topology we could put on Y that will satisfy this property that we stated in the lemma. To see this, you just need to draw the following special case of this pink diagram on the right, namely where we have the map Q going to the space Y twice. However, here on the right, we're going to consider Y with the standard quotient topology, which I'll call tau Q. And here on the left, we're going to have some other topology, tau prime, on Y. However, we assume that both of these topological spaces, Y with the standard quotient topology tau Q and the space Y with the non-standard topology tau prime, that both of these satisfy this lemma. Okay, now what can we deduce? Well, we can always put the identity map here, which is a priori just a function. However, we can observe that this map Q here is equal to Q after the identity. And we know that this quotient map here, Q, is continuous. And now by hypothesis, because both of these spaces satisfy this lemma above, this means that also the identity map in this direction is continuous. Okay, but what does that mean? Well, an identity map being continuous will imply the containment of one topology in the other. Why is this? Well, take some open set U that lies in this tau prime. We know because the identity is continuous that the preimage of U under the identity must be an open set in the space Y with the topology tau Q. So this means that if we have an arbitrary open set in tau prime, it must also lie in tau q. So in this case, the identity being continuous means that tau prime is a subset of tau q. Okay, so I'll mark this up here. We conclude that tau prime is a subset of tau q. Okay, but this argument is symmetric in the sense that we could have also chosen the identity map going in the other direction. And now basically we use the same fact that q is q after the identity, but now with the other quotient map, and this q is also continuous. So this other identity is also continuous, which will now imply the reverse inclusion. So this means that tau q is contained in tau prime. So in fact, tau q is equal to tau prime, meaning that the two topologies coincide, and we've now shown that the quotient topology is the only topology that we could possibly put on Y that satisfies this property in the lemma. All right, so that's pretty nice because this is like a property that we'll want for a quotient space. And this is telling us that there's basically only one way we could have defined the quotient topology on Y in order to get this property, so there were never really any choices involved. Now that we've proved this lemma, we can finally move on to the universal property of quotient spaces. We again have a similar setup. We have a quotient map Q going from a topological space to the quotient space Y. And now we, in addition, consider a continuous map going from X to some topological space Z. And moreover, this continuous map should be constant on the fibers of Q. What does this mean? It means that whenever the map Q identifies 2 points, then so does this map F. In other words, if Q of X is equal to Q of X prime, then also f of x is equal to f of x prime for all pairs x, x prime in the space X. Okay, now under this setup, the universal property of the quotient space will yield a unique continuous map, f tilde, going from Y to Z that makes this diagram here on the left commute. So again, recapping using this diagram here, the setup we start with is the space X and a quotient map Q going to the quotient space Y, along with an additional continuous map F going from X to a space Z. And moreover, we assume that whenever Q identifies 2 points of X, then so does F. Under these assumptions, there exists a unique continuous map F tilde going out of the quotient space into Z that makes this diagram commute. Intuitively, you can think about this situation as follows. We start with some space X, and we identify certain portions of X to obtain a smaller quotient space Y. So we've smushed or glued together certain parts of X to obtain the space Y. And now we'd like to define continuous maps out of this smaller space Y. However, these identifications we introduced in taking the quotient might be very complicated, so it could be difficult to directly define a map out of the quotient space. However, it might be more easy to define a continuous map out of our original space X. Now the universal property is telling us that as long as this map we define out of X, so this map F, satisfies this property here, so it means that whenever things are being identified by the quotient map, then they are also being identified by F. Or in other words, we could say that F respects the identifications that we made by taking the quotient. Well, in this case, this map descends to this quotient space Y to give us a unique continuous map going out of the quotient space. We'll see a concrete example of this later, but for now, we'll focus on proving this universal property. In fact, this proof will almost exclusively use set theory rather than like things in topology, because the only part that uses anything from topology will be showing that this unique map that we obtain is continuous. And this will follow from the lemma we had previously. However, the existence and uniqueness of this map f tilde is a purely set theoretic thing. And you may have encountered this situation before when thinking about functions out of sets of equivalence classes. Okay, so let's assume all of these hypotheses that we are given in the universal property statement. In particular, we'll assume the fact that if 2 points are being identified by Q, then they are also being identified by F. All right, so now we want to define a map f tilde going from y to z given the maps Q and the map F. So what we're going to do is we're going to define f tilde of a y and y to equal f of the pre-image of y under Q. This is really the only thing we can do given the data we have. However, there are two issues here. First, there's the issue of whether this pre-image under Q of y is non-empty, but this is the case because Q is a surjective map. So I'll note this here. So this is non-empty because Q is surjective. So really for any point y and y, we can pull it back to its pre-image Q inverse of y. This deals with the first issue, but now we still have the issue that this pre-image here may contain multiple points, so we don't necessarily know how to map this set to z using f and get a unique point in z. Another way of saying this is that in general, if we have an arbitrary function going from x to z, this arbitrary function might map the points in this pre-image to different points in z. And in that case, our result would depend on which point in the pre-image we choose. However, because of this assumption we've made here, it turns out that f will map any point in this pre-image to the same point in z. So I'll write this out here and then I'll show why this is the case. So f maps any, let's call it small x, in the pre-image of y to the same z in capital Z. To see why this claim holds, we'll let x and x prime be elements of the pre-image of y under Q. Well, this implies that Q of x is equal to y and also Q of x prime is equal to y. So in particular, Q of x is equal to Q of x prime. And now this means by our assumption that also f of x is equal to f of x prime. So indeed, any 2 points in this pre-image Q inverse of y will be mapped to the same point by f. And this means that regardless of which point we choose here in this pre-image, it will be mapped to the same point in z. So this definition here is well defined. If we wanted to be really precise, this notation I've been using here is maybe not the most correct. So this pre-image of y under Q, this is a set. And if we map a set using f, so we consider the image of a set under a function, this will again be a set. But in this case, what we've shown here is that this is actually a singleton set. So it means that we just choose the value of f tilde of y to be the unique element in this singleton set. If you want to think about this process in terms of this diagram, if we want to find out where we map a small y in the set capital Y using f tilde, what we do is we first pull back this point along Q to some arbitrary point in the pre-image and then map that point forward to z. And this assumption here ensures that regardless of which point we chose to pull it back to, the result will be the same, and so it really doesn't matter which point we choose. So far, we've shown that under the hypotheses above, there exists a function f tilde from y to z. It now remains to show that this function satisfies this equality here, but that follows more or less straight from the definition. Why is this? Well, if you map a point x using this composite f tilde after q. What is this? Well, it's f tilde of q of x. But this, by definition, is f of q inverse of q of x. Now let's think about what's going on here. So this means that we're mapping some point x in x to y via q, and then looking at the preimage of the point that we mapped to. So in this case, this y is actually a q of x, and this preimage up here is actually q inverse of q of x. Now it's not necessarily the case that if you start with an x, you map to q of x and you take the preimage, that preimage will only consist of the point x. In general, it can consist of more points because we're actually identifying certain points using the quotient map. However, using this assumption here, we've seen that any point in this preimage will be mapped to the same point in Z under f. In particular, x itself lies in this preimage, so the image of any point in this preimage will be the same as the image of x under f. So this means that this here actually corresponds to f of x. And hence we've shown that f tilde after q of x is equal to f of x, and this holds for all x, meaning that these two maps are actually equal. All right, now the final thing to show about this function is that it is unique with this property that it equals f if you compose it with q. For this, we suppose that there is some other map going from y to z, which I'll call g, with the same property as f tilde, namely that f is equal to g after q. All right, but we know that f is equal to f tilde after q, so this means that g after q is equal to f tilde after q. But from this, it now follows that g is equal to f tilde by the fact that q is surjective. I'll explain in a moment why this is the case, but it's a nice fact to remember that if you have a surjective map, it means that you can cancel it on the right with respect to function composition. To justify this implication, we suppose that there exists a point y where g and f tilde don't coincide. So we have some y in the set y such that g of y is not equal to f tilde of y. Now, because q is surjective, there will be a point in x that is mapped to this y by q. So we know that there exists an x in x such that q of x is equal to y. But this now shows that g of q of x is not equal to f tilde of q of x. However, this contradicts our assumption that these two composite maps are the same. So essentially, we can cancel surjective maps on the right because any counterexample to the fact that the two maps in question would be equal can be pulled back along the surjective map to provide a counterexample that the two composites would not be equal. Again, this is something that you should think about more for yourself, and you can also think about how to prove that injective maps cancel on the left. In any case, we've now shown that given the hypotheses in this universal property, there exists a unique function, f tilde, going from y to z. However, we have not yet talked about the continuity of this function. But here's where this lemma we proved in the beginning comes in. We know by what we've just seen that f is equal to f tilde after q. Moreover, we know that this composite here is continuous because f is continuous, and we know that q is continuous. And now by the lemma we proved previously, this implies that f tilde is also continuous. Together, we've now shown all the facts that this universal property claims, namely that given a quotient map q from x to y and a continuous map f from x to z that respects the identifications that q makes, there exists a unique continuous map f tilde from y to z that makes this diagram here on the left commute. Let's illustrate the universal property we just saw with the following example. So the example is R mod z. So this is the real line quotiented out by the equivalence relation that is given as follows. So x is equivalent to a point y if and only if x minus y is an integer. So for example, 3.3 would be equivalent to 5.3. If you want to see this pictorially, you can think about the real line as being coiled up as a helix, like this, where 2 points lie above each other exactly if they are separated by an integer distance in the coil. So this would be some point x, and up here we'd have the point x plus 1, and then one further up we'd have x plus 2, and so on. And the point being that all these points that lie above each other, they are being identified in this quotient. And while using this picture, it's kind of obvious that this thing is basically just a circle. But this fact is something that one would have to prove using properties of quotient spaces. In any case, the setup we have for this space is as follows. We have the real line, and then we have R mod z, and we have this quotient map, which is given by the identification provided by this equivalence relation we've specified above. Okay, and now what we're going to do is we're going to consider some map going from R to itself. In particular, we'll consider this map here being f of x is equal to sine of 2 pi x. Now what we're interested in is obtaining a map out of the quotient space R mod z, so that's an f tilde, that makes this diagram commute. Now, by the previous universal property we saw, the only thing we need in order for us to be sure that such a map exists is that f preserves the identifications that q makes. Or in other words, we need to check the condition that q of x equals q of x prime, that this implies that f of x is equal to f of x prime. Okay, so that's something that we need to check. Okay, but by the way I've defined these maps, this is pretty simple. So if q of x is equal to q of x prime, by the definition of this quotient, this means that x minus x prime is an integer. Or another way of writing this would be to say that x is equal to x prime plus n, where n lies in the integers. Okay, but now we need to check whether f of x is equal to f of x prime. So we write out f of x is equal sine of 2 pi x. But now we use the fact that x is equal to x prime plus n. So we get sine of 2 pi times x prime plus n. Okay, we can expand this to be sine of 2 pi x prime plus 2 pi n. And now using the fact that sine is periodic with period 2 pi, this is just the same thing as sine of 2 pi x prime, which is equal to f of x prime. So you see that the way I've set up this function f is done in such a way that it satisfies this property, so that we've checked that. And this means that there exists a unique map f tilde going from R mod z to R that makes this diagram here commute. In practice, we can use this as follows. So we consider the equivalence class of some x in R mod z. To be concrete, we could maybe look at the equivalence class of 0 in R mod z. Now, where is this mapped using f tilde? Well, it will be mapped to f of 0, which in our case is sine of 2 pi times 0 is equal to 0. Why is this? Well, for example, the point 0 in R is mapped to the equivalence class containing 0, and also 0 is mapped to 0 using f. And now we can use the fact that this diagram commutes to conclude that the equivalence class of 0 is mapped to f of 0, which is equal to 0. On the other hand, we could have also chosen some other pre-image of the equivalence class of 0 under Q. For example, we could have chosen the number 1. Well, in this case, we would have determined that the equivalence class of 0 is mapped by f tilde to f of 1. But this is, again, sine of 2 pi times 1, which is also equal to 0. So the whole point of this universal property is that it doesn't matter which pre-image you choose here, you'll always get the same result. So this gives you a concrete way of determining where a certain element in this quotient space is mapped by this map f tilde that we get from the universal property. You just see what the pre-image, or one possible element of the pre-image, is in the original space, and then map that using the map f. Okay, so this shows how you can use the universal property of quotient spaces in concrete cases. Now there's an additional problem posed by this picture we drew over here. Namely, we saw that the space R mod Z intuitively looks a lot like the circle S1. Now it would be really nice if we had some easy way to show that these two spaces are actually homeomorphic. And this will be precisely the content of the next proposition we'll have a look at. For this, we have the following setup. We suppose that we have two quotient maps going out of X. So we have a quotient map Q1 going from X to a quotient space Y1, and a quotient map Q2 going from X to a quotient space Y2. And moreover, we assume that both of these quotient maps make exactly the same identifications. So if 2 points are identified by Q1, they are also identified by Q2. And conversely, if 2 points are identified by Q2, then they're also identified by Q1. In this case, these hypotheses are sufficient to deduce that the two quotient spaces must be homeomorphic to one another. So I'll just draw this picture quickly. So we have a quotient map Q1 going from X to Y1, and a quotient map Q2 going from X to Y2. And now we're going to try to prove that these two quotient spaces, Y1 and Y2, are homeomorphic. And this follows pretty much immediately from the universal property. So we assume that this equivalence here holds, namely that Q1 makes exactly the same identifications as Q2. We're now going to use the universal property for quotient spaces twice. First, we observe that because Q1 of X equals Q1 of X prime implies Q2 of X equals Q2 of X prime, this is exactly the condition we need to obtain a unique continuous map going from Y1 to Y2 that makes this diagram commute. So in the notation we had in the universal property, this map would be called Q2 tilde. And it satisfies the equation that Q2 is equal to Q2 tilde after Q1. Okay, and now using the other implication, namely that Q2 of X is equal to Q2 of X prime, implies that Q1 of X is equal to Q1 of X prime, we also have a unique continuous map going in the other direction, which is Q1 tilde, such that Q1 is equal to Q1 tilde after Q2. So the situation we've created here is the following. We have maps going from Y1 to Y2 and Y2 to Y1 that are continuous. And because we're trying to show that Y1 and Y2 are homeomorphic to one another, we want to show that these two maps are actually inverse to one another. Okay, so let's start with the first equation we need to show. So we'd like to show that Q2 tilde after Q1 tilde is equal to the identity, and in this case it's the identity on Y2. So I'll mark a question mark here because we don't yet know that this is the case. However, we already have some equation which kind of looks like what we want over here. So we have Q2 tilde after Q1, but from the equation over here, we know that Q1 is equal to Q1 tilde after Q2. So we can just expand this like like so. And we get this equation that Q2 is equal to Q2 tilde after Q1 tilde after Q2. Okay, but we can also insert the identity here. In this case, it's the identity on Y2. And this equality will still hold because composing anything with the identity does nothing. And finally, what we're going to do is we're going to use the fact that surjective maps like Q2 are right cancelable. So this is something we saw before in the proof of the universal property. This equality here, identity of Y2 after Q2 is equal to Q2 tilde after Q1 tilde after Q2. We can cancel Q2 on the right and obtain the fact that the identity on Y2 is equal to Q2 tilde after Q1 tilde. And this is exactly what we wanted to show here, so this equality actually holds. Now, another way to think about what we did here, canceling Q2 on the right, is using the fact that maps we obtain from the universal property are unique. So note that here we also have the identity on Y2, and the identity on Y2 is a continuous map, and moreover, it satisfies the equality that Q2 is equal to the identity after Q2. On the other hand, this map here, this Q2 tilde after Q1 tilde, is also a continuous map that satisfies that Q2 is equal to, well, this composite Q2 tilde after Q1 tilde after Q2. However, in the universal property we saw that continuous maps with this property are unique, so this means that in particular the identity has to equal this composite map here. Of course, in the proof that we gave for the universal property, we used precisely this right cancellation property of surjective maps, so it's not surprising that we can just do that directly here as well. In any case, regardless of how you think about obtaining this equation, we see that we have 1/2 of what we need to show that these two maps are inverse to one another. Okay, but now we can observe that the situation in this diagram is completely symmetric with respect to the indices 1 and 2, and we could have done exactly the same thing, just replacing Q1 by Q2 everywhere. So this means that also the identity at Y1 is equal to Q1 tilde after Q2 tilde by symmetry, and this together shows that these two maps are inverse to one another, and now that we have continuous maps inverse to one another, which means they are homeomorphisms. All right, so we've proved the fact that Y1 is homeomorphic to Y2 by using the universal property twice, and this required the assumption that we can go from this identification here to such identifications and conversely. I'm aware that this argument is kind of abstract because we're using this abstract universal property, and you should, if you don't understand this, you should really go through it slowly by yourself again to see that you can also derive this result. In particular, this type of argument occurs constantly when you're working with universal properties, so it's good to have looked at it in detail at least once. The upshot of this uniqueness of quotients is that it gives you a way to prove that two quotient spaces of some common base space X are homeomorphic to one another. So the situation you have to imagine is that you have some base space X, and you define some quotient space in one way, and you define the second quotient space in another way. However, as long as both of these ways of defining the quotient make the same identifications of points in X, the resulting quotient spaces will be homeomorphic to one another. To illustrate this, let's now show that this quotient space R mod Z we looked at previously is actually homeomorphic to the unit circle. Okay, so the setup is as follows. We have this quotient map, which I'll call Q1, going from R to R mod Z. And we have the quotient map Q2 going to S1 from R. And this Q2 is actually the exponential map e to the 2 pi I x. And as a reminder, Q1 identifies 2 points precisely when they differ by an integer. All right, so now to show that these two spaces are actually homeomorphic, we need to show that Q1 and Q2 make exactly the same identifications. So first, we suppose that Q1 of x is equal to Q1 of x prime. Well, by definition, this means that x minus x prime is an integer. Okay, but this means that e of 2 pi I x is equal to e of 2 pi I x prime, because this exponential function here is periodic with period 1. This is precisely the same argument we used before to show that the sine of 2 pi x is periodic with period 1, and in the case where these two x and x prime differ by an integer, we'll get the same value if we insert them into a one periodic function. Okay, but by definition, this is just Q2 of x, and this is equal to Q2 of x prime. All right, so we've shown one direction. We've shown that if Q1 identifies 2 points, then also Q2 will identify those 2 points. So this already gives us some unique continuous map going from R mod z to S1. Okay, conversely, let's suppose that Q2 of x is equal to Q2 of x prime. Well, this means that e of 2 pi ix is equal to e of 2 pi ix prime. And now by properties of this exponential function, this implies that x is equal to x prime plus some integer n. You could prove this in more detail, but recall that this complex number here represents a number that has distance 1 from the origin and has angle 2 pi x from the x-axis. And well, angles 2 pi x equals 2 pi x prime. So as angles, these will be the same precisely when x differs from x prime by an integer. Okay, so continuing our argument here, we have now found that x differs from x prime by an integer, which means that Q1 of x is equal to Q2 of x prime. And this shows the equivalence we need in order to get a second map in the other direction, which by the argument we gave in the previous proposition is actually going to be an inverse to the one we had before. Okay, so these 2 points together show that R mod z is homeomorphic to S1. So I hope this illustrates why all of these abstract properties can be very useful, because this proof was really fast in comparison to trying to do this directly by constructing certain continuous maps which are homeomorphisms. And in principle, to apply this type of argument, you don't even need to know what the quotient spaces look like. All you need to know is what identifications you made in order to arrive at a given quotient space. Now there's one sort of difficulty which I glossed over in this argument, which is that the prerequisite to use this argument is knowing that both of these maps here are actually quotient maps. So this argument does not work in general if you just have some surjective continuous maps here. They have to be quotient maps. Otherwise, the whole universal property doesn't take effect, and the subsequent argument on the uniqueness also doesn't hold. Now, in the case here on the left of R mod z, we defined this essentially as a quotient given by this map Q1 making the identifications given by the equivalence relation we defined in the beginning. On the other hand, here S1, we actually look at as a pre-existing space, and we have this exponential map going from R to S1, but in principle, we have to first check that this exponential map is actually a quotient map from R to S1. I didn't do that here because we did it in a previous video, namely in the second video on quotient spaces, but this is something you need to do if you wanted to use this argument from scratch. So in some sense, the fact that this proof of this homeomorphism here was so easy is because we left out the hard part of showing that this Q2 is a quotient map. However, we also saw in the previous video that if we have a map that is surjective and either open or closed, it is automatically a quotient map. And in many cases, checking openness or closedness of maps is actually not so difficult. Therefore, this method of proving homeomorphisms between quotient spaces is actually a significant simplification of doing it directly. Finally, I'd like to remark that all of these spaces here are actually also groups. So R can be considered a group under addition, and so can this group here, R mod Z, which is actually the same as quotienting out the group R under addition by its subgroup of the integers. Finally, S1 can be considered a group under multiplication of complex numbers. So in this case, you would multiply two elements on the unit circle, and you get a third element on the unit circle, whose argument is the sum of the arguments of the original elements. This is because the exponential function, if you multiply two exponentials together, it converts products into sums. So not only are these two spaces here homeomorphic as topological spaces, they're actually also isomorphic as groups. And if you're familiar with some group theory and the universal properties for quotient groups, you can think about how those relate to the universal properties we saw here for topological spaces. To give away the punchline, basically everything works exactly the same way as it works for topological spaces, just you have to replace continuous maps with homomorphisms of groups and, well, quotient spaces by quotient groups. And in that case, you can make precisely the same argument with the groups as you can with the topological spaces to show that these two things are isomorphic as groups as well. And this is one of the powerful ideas behind using these universal properties. Essentially, they are able to span multiple types of objects, and you have the same types of properties for these different types of objects. And so in many cases, arguments, say for topological spaces, can be converted into arguments about groups and vice versa and so on. All right, so that concludes what I wanted to say about quotient spaces. In the next video, we'll be looking at adjunction spaces, which are special types of quotients that can be used to glue two spaces together along a certain function.